Let's now finish the presentation for this week on the bias-variance trade-off. So when we are talking about bias-variance trade-off, we are talking about looking at something, at the decomposition of the error that we have when we are using, for example, the quadratic error. So if we are looking at the expected quadratic error, so basically we are looking at what we expect as difference between the let's look at the difference between the theta and c squared. We can develop this that way. So basically, if we are getting back to the quadratic error that we have before, so if we are looking at this thing, which is the quadratic error that we were using for regression here, the expectation of that error over given some x can be decomposed as two components. So we have first the impact of noise here, which is that part. And we also have the really quadratic error by itself in terms of the prediction without the noise. So kind of we are able to get the noise out of this formulation. The point is that the noise does not depend on H. So we cannot remove it. It is not based on the data by itself. It is in the data, but it's coming from the phenomenon. So we should somehow not care. We will never be able of getting an error of 0 unless we have a noise-free data set. But the quadratic error by itself, this is really where we are looking at whether the prediction made by H are really correct, close to what we expect in terms of values. So we are looking at the difference between the expected R minus the H of X, according to a X value that we are on which we are working. So we say for a given X, we expect as a value of R, a given R. There's not really a specific R. This is the expectation of R that we are looking for. That's why we are formulating this that way. And we are comparing this with the prediction that we are making on that. And we want to minimize this. We want the H to be as close as possible as the really what we expect as R value here. So we can look at the average of H over all possible data sets. So we say that, well, our data sets are following are coherent with the likelihood of R and X here. So we can look at the expectation over all data sets, like we used before with the bias-variance decomposition, the decomposition we had before. And so the expectation over all data sets of the expectation of R given X minus the prediction squared can be developed as the bias squared plus the variance. So basically, we are looking at how bias is our prediction. And this thing, usually if we have a strong model enough, the bias should be relatively small, equal to 0. And the variance is something else. The variance is really about the variation of the H versus what we expect as H in the overall data sets. One way to see it is with that diagram. So we can see like the 4 different cases. So let's say we have the first case on the top left, which is high bias and high variance. So that's the worst one. That means that okay, the target is really to be really bullseye on the center here. We want to be at the center of the target here. This is what we are looking for. But in fact, we have a bias, because if we are looking at this thing, we can see that on average, it is somewhere off. So there is some distance between what we want as target and what we obtain here. So this is a big bias. And over that, we have also a huge variance because the points are spread out in a big zone. So they are kind of spread, so the variance is also important. And you look at this in terms of the estimating the parameters. So when we estimate the parameters that way, that means that we've got parameters that are quite off the good parameters. And from one time to another, from one data set to another, coming from the same phenomena, the estimation may be quite different. So this is not good. This is what we don't want. We have another case where we have an high bias and low variance case. So that means that, yeah, on average, if we're looking at the average value of the estimator versus what we have at target, which is the ground truth usually, we have a big gap. So we have a big variance, a big bias here. But in terms of spread, the points are relatively close together. So the variance is low, but the bias is important. That's typical of models which are not complex enough. The models has their own bias, and this bias made the models unable to fit well the data set. So we are always off in some ways, which is a good bias, but we are coherent from one data set to another. We always get something that is relatively coherent. So the spread of the points is relatively small. So this is a case of underfitting where our model is not strong enough for our data set. We have another case, the opposite case, which is a low bias, high variance case. So in that case, we see that the average of our predictions, the black dots here, are relatively close to our target. We have a small difference, so the bias is kind of small, but the spread is big. That means that on average, if we are looking at all the models we can get over all the different data sets coming from the same phenomena, we are on average fitting well, but each specific models can vary a lot. So we can get a lot of variation. So we can get individual models, parameters from one specific data set that may be quite off what we are looking for. So this is typical of, I would say, the opposite case, where we have models that are too complex for the data set we have at hand. So it tends to overfit, it tends to memorize the data somehow pretty well. So being off the general model that is underneath. So it's really good on the specific data, but it doesn't generalize well. And then the last case is the best case. This is what we would like to have in all cases: low variance, low bias. So it means that we are on average quite close to the center and the spread is small. So we are usually quite consistent. We usually get about the same kind of results from one data set to another coming from the same phenomena. So the generalization here will be good. So we have some example of bias-variance trade-off. Let's assume that we have different data sets. We have xi, which is one data set, and we have m of these. So let's make an experiment with that. Let's see that we are able to generate data sets on demand, and that is coming from the same noisy function. So each of these data sets are coming from the same function, but this function is noisy. In practice, we don't know the f function, so it's not possible. But here, it's really a good way to illustrate what's going on by a function that we completely control. So we will make a control experiment to illustrate this point. And we see that we obtain the hi from the training data set. So we are making a training of hi on xi. So we are able to train different models on the different data sets. And what we are looking is at the expectation, for example, of x. So we say over all the hi, so expectation over the data sets, what is the average model that we have? So we are looking at the average prediction here. We will make the sum of the predictions for a given x over all the models that we obtain over all the data sets that we produce. So from that, we can compute the bias squared. So no, not squared, bias power of, yeah, squared, sorry. So bias squared here. So we have the new bias here, which is the difference between the expected h that we compute with this minus the real value that we get from that function without the noise. And then we look at the difference squared here. So this difference gives us the bias. And likewise, with the variance, we are looking at the difference between the predictions for each model versus the average prediction over all models. This is squared. So, and we do this over all data sets model, all samples. So with an h of I, for example, if we go in an extreme case, we have an h that is simply a constant. We just set up a constant. So we have a zero variance case here. So basically, all these things will get to zero because all the h will give the same value, c. But it is underfitting. It is not strong enough. Conversely, we can go with, we can go now with more complex settings. For example, using the average of our values over our data set, they will reduce the bias, but will increase the variance a little, and so on. So when we get low or no bias, but high variance, this is typical of overfitting. So we can use this to see different model, use as HI, and see what's going on in terms of bias and variance. So let's go back to our polynomial regression example. So we have some data here. We know that the blue line here is basically the real function f. And the black points are example of points obtained with noise. So these are points sampled from that curve plus some noise. If we are looking with polynomial of degree 1, so basically in our equation, we've got this bunch of results, which are, I would say, polynomial of degree 1 here. We have polynomial of degree 3 here, which are more complex. But still, you know, these two are not fitting well. These are not really what we are looking for that thing. We have polynomial of degree 6 here, which seems to be quite good, which seems to be fitting really well. And then we have these two cases, you know, this polynomial, you know, they are really good in that zone. But on the more extreme, at the beginning, maybe more with the lowest and the highest values, there seems to be a lot of variation, especially here. You could see that this goes really badly at that point. Likewise, here it goes quite badly. So it means that we are not that good outside the zone. So we have a lot of variation here. This is typical of high variance situations. We can even trace this curve. So basically, it's the error of our model. We see here that the black curve is the mean square error. So at first, you know, it goes down, and then it starts to goes up a little. Because at first, the main component here, don't forget, it is a log scale here. So basically, on the y-axis, it is log scale. So it's you need to be cautious with that. And so I would say the first part here, the main component of the error is the bias. That is the zone where the model is too simple for what we want to do. So we have a high error, high bias case. And on that part here, we see that MSA is basically the variance. So this is the place where we get, I would say, variance as the principal element. We see that the bias is really low here. And we see that, in fact, where we have the lowest error is at that point here with a degree of 6. So at a degree of 6, we have the lowest error. And if we go more on with higher degrees, we can see that the error is increasing a little. It's not that big, but it's still there. It means that we have overfitting. We have two complex settings, two complex models to fit the dataset. So that illustrates well the trade-off. That means that we should keep being in that zone. This is the zone where the error will be minimal, and this is where we will get the best trade-off in terms of generalization. And then if we are looking also at the train versus test, this is the same kind of things that we were looking before. But now it's kind of obvious that we've got a problem in terms of generalization here. We see that at first, you know, we get better and better in terms of performance. But after some point, you know, okay, here the train errors be quite low, even though it increased a little, but the test error is kind of skyrocketing here. So if we have really huge test error, it means that we are not generalizing well. We'll get big errors with higher order polynomials because with new samples coming from the same phenomena but not used for training, we will be relatively bad. So here again, we can see that the sweet spot is in that zone. This is the zone where we will get the best performance. Well, we will generalize well. Look at the test error here, which is the lowest at degree 6. But of course, in practice, we could use a test set as part of our training set, but the real test set, which will be in deployment, is not accessible. We will need to see it after. So in practice, we cannot calculate the bias and the variance of a model. This is not something that is possible in practice, but theory can be made on that. We can demonstrate that some models are really good in terms of bias variance trade-off and all these things. And in fact, I would say in practice, the real thing to look at is the cross-validation. You know, it's computing the performance on a part of the dataset that is not used for training. So this is really a good way to empirically measure the generalization of our model. One way to deal with that is to make use of regularization, and we will get back on that often during the course. This is super important. Regularizing means to optimize not just according to the empirical error or to some kind of loss functions. It's also to include the model complexity as a parameter that we can adjust. And we want to find a trade-off between having the right model and reducing the error. So we want to figure out the model that is complex enough, but not more complex than what we need to get good performance, such that it will ensure some generalization capacity. So in that case, we are using often the parameter lambda. It's not always lambda, but it's one way to name it. This is a parameter that is making the trade-off between the empirical error measurement and the model complexity measurements, which are often not at the same scale and not with the same type of measure. So in order to adjust them, we need to have some kind of lambda, and this lambda is often adjusted empirically. So just usually by cross-validation, we try to find the lambda that give us the best performance on unseen data instances. There are different kind of measure of complexity. There is like the Vapnik-Chervonenkis dimension that was widely used in terms of computational learning theory. It has been used to support SVMs, all these things. So this is an interesting measurements that is really evaluating how strong is the model in terms of being able to classify and to be able to fit over complex data that are intertwined, and how much it is able to separate them. We also have other things based in information theory, like the minimum description length. So this is like how many parameters we need to describe our model. So we assume that with less parameters, the model is simpler.